Hello, my name is Mary Grygleski. I'm a senior developer advocate at IBM. I'm with the WebSphere and Liberty engineering team. And I'm an advocating for Java, cloud, and open source, and specifically too with Open Liberty. That's the open source WebSphere that IBM works on, is an open source project. And in fact, I'm involved with all Java and open source projects, and also the cloud too, getting into Kubernetes and all that. And so I'm very happy to be here at Techno Day and celebrating the International Women's Day. And it is a really great opportunity to be sharing with everyone. And my title today is Paradigm Shift from Imperative to Reactive in Java. And I'll start. So essentially, too, I won't have enough time to get into the whole topic. And as such, if some of you have already been working with reactive technology, be it programming or working with the reactive systems, and you'll realize that it is a topic that seems to be like can cause confusion, but also a lot of excitement because of what it can promise. And it's not something, for the faint of heart, so to speak. And you'll find that if you get into reactive, it does require you a paradigm shift in the change of how you think about solving problems in this domain. So I just put this slide in here. I call it reactive and event-driven computing in a nutshell, because I'm going to be giving you an introduction on this topic. And so let's start. So what is reactive? So first of all, I like to clarify too, when reactive first came out in the 2010, like early 2010, at the time too, there was already JavaScript that's React, I believe. And then there's also reactive framework, which actually on the Java, or actually I should say, on the reactive side is more catered for more enterprise computing, reactive. It first came out, there's RX.NET, so reactive extension, and that's came from Microsoft. And then in the 2011, or actually I should say 2000, year 2010 or 11, yeah, that time frame, Netflix came out, and they also were trying to search for a library, or they trying to come up with some new ways of solving problems that has to do with concurrency, that has to deal with asynchronous processing, things of a more event-driven nature. And then they came across reactive extension, and that's the Microsoft RX.NET. They found that it is actually very close to what they're looking for, so they eventually ported RX.NET to Java. So that's when RX Java came out. When it first came out, it was RX Java was more popular too with Android development, with mobile Android, and naturally speaking too, in mobile computing, the need for like real-time communication is a lot even more pertinent, because when we're on our devices, we want to make sure that whatever we're doing, the apps has to be very responsive. It can't take a long time to process, because these are the small devices. We want it to be almost like instant all the time. So go back to this question, what is reactive? It kind of conjure up a lot of different responses. People might be thinking of, oh, reactive, that's React Java, React Native. Yes, in some ways too, those libraries in JavaScript, they are aiming to solve a problem that are kind of similar, but fundamentally, it's really what we're looking at for reactive is the fact that we want applications to be very responsive. There's not much a delay, there's not much latency, so to speak. So highly reactive, highly responsive. And the thing is too, in the Java world, that's where I'm focusing today's topic on, is that reactive in the Java world is essentially too, we can kind of broadly categorize into like three kind of subtopics around this. Essentially, there's reactive programming, and then there's reactive systems and reactive streams. And also, too, as you can see, I'm using some fruit here, because it's like, I just want to talk about like reactive, even though these are reactive, but they are kind of like fruit, right? You look at them, they're like, oh, they seem to be all like from the same family of fruit, like plums and apricots and peaches and, kind of nectarines, those things, but they are really not the same. I mean, they're kind of somewhat like from the same category, kind of, way of kind of categorizing them, but they're different. So let's take a look. There's programming. So let's take a look at that first. Reactive programming. Okay, so when we talk about reactive programming, we're really talking about data as streams. So in the traditional way, right, and that's why my topic too is talking about paradigm shift from imperative to reactive. Imperative, really, what it is that when we do programming, and that's essentially how we are all, I believe most of us, or if not all, when we first started programming, we would be learning things the imperative or traditional way. So say, for example, you're doing things and we know that it's kind of sort of almost like a sequential way, right, of solving problems. We're dealing with problems that, we issue a command and then we wait for the request to come back. So there's implied this synchronous kind of nature. There's what we call, on the thread level is that it involves the blocking. Because threads are essentially they are used to be too hardware, right? Used to be single CPU, which actually makes the computing a lot kind of simpler in some sense, in which you only have a main thread and the thread is handled in the kernel, kind of like that. So now the thing is that then in reality is that that's not how we do things. We need to be doing things all at once, or doing many things all at once. We can't just be sitting, and so that's when the idea of like concurrency, all of these like complex computing kind of came out. Is there some better way of able to utilize these computing resources and handle them and making it to be very efficient? So that's when, like, okay, so back to this whole thing is that reactive programming. So we're then dealing with data as streams. So in other words, too, is that, all the computer scientists is like trying to figure this out. It's basically reactive programming is just one way of solving this problem. But in some ways, too, reactive programming involves extremes, viewing data as streams. So you're processing data. And it also implies to this event-driven nature of computing. That's actually also very asynchronous in nature. And what does it mean by asynchronous? That means, when you issue a request, there's no need to wait. You have a request that comes in, and basically, on a threading level, then, it's essentially too, in some libraries too, in which there are event-driven, there's like an event bus. For example, in Eclipse, Vertex library, the event bus essentially, pick up your request and then go and does its own thing and take care of things. And in the meantime, the user too, while I'm the one that issued the request, I don't need to wait around for the processing to be happening. In the meantime, I get free up. I can go off and do some other things while, my request is being processed. So in other words, it's a very efficient way of handling on problems on the programming level. So let me then come back to this slide. So there's reactive programming, and very often too, when we address reactive programming, we make use of what is called like these streams, and so we use these lines to represent streams. So in this particular case, it's an example of a very kind of a common usage is, and what we call too is that when we work with data that's in stream, we call that operator. And not to be confused, these days when we're working with cloud, with Kubernetes, for example, we also have operators. But this operator, what we're talking about is it operates on streams of data. So that's like in reactive programming in that kind of this computing space. So these are like called map. In this case, is an operator that operates on a reactive of a stream, a data stream. So this example is showing that map, as an operator, it's also makes use of the functional style of programming. And also, I wanted to point out too, functional programming and reactive programming are not exactly the same, even though reactive programming makes use of the functional style of programming. So in Java, since Java 8 came out with streams programming and lambdas and all those goodies, right? In the Java 8 lambdas and streams and functional style of programming, it really greatly eases the transition to go into reactive programming. So now this is how we do it. This is an example of an Rx Java operator. And actually, even with this operator too, because Rx reactive extension has been ported to many languages too. Maybe some of you are already working with Rx JS, the JavaScript, Rx Ruby, Rx Python, Scala, Rx Kotlin, you name it, right? It is there. There's port in there. So in this particular case, we're looking at, say, a Java example. And the usage would probably be somewhat similar among other languages too. So you see there's a map. So I wanted to also kind of go back to functional programming. So functional programming is not the same. It's because in strictly speaking, in the functional programming, we're dealing with, your program, you have your thread of execution. So it's basically your thread, that's what drives the data forward, is that your thread is operating, or kind of processing. And so the data will be changed, the state will be changed. So then that's how you cause the flow of your program. Whereas in reactive programming, it's slightly different. We have to think a bit more abstract way, is that we're dealing with data that's actually carried by the stream. So anytime too, your program, how it advances is when the state of the data gets changed in the stream. And that's what drives your flow of your program. So it's kind of slightly different, even though you might say, well, it is still dealing with data, but still the idea is different, because functional programming is basically your thread is operating. It could be like, operating on different data too, than you're dealing with. So once, some changes in some data state, then your flow of your program keeps going. Whereas in reactive, it's the state of the data that's carried by the stream that gets changed, and that's when it actually causes the flow of the program. So enough of that. So let's get back. So in this example is that I'm using like map. So map essentially is like a function. So think of map function, right? You basically define the function. In this case, x is equals 10 times x. So which means that in this case, for Rx, in an Rx Java format, we're using an observable. Observable is what kind of takes in your stream, your data stream. So in this case, doing a dot just will essentially take in the input. In this example, we're taking in 1, 2, and 3. And then we apply this operator of map operator to it. And the map operator basically tells it, okay, whatever inputs come in, I'm going to multiply by 10. So then it finds these data on the stream. Then essentially too, within the same program statement too, that's another nice thing about functional reactive style of programming, is so efficient. You can do multiple steps, of processing all within one statement. So, and if you have been following like Java, especially if you kind of watch some speakers talk, right? There's Dr. Venkat, he's a well-known Java speaker, great person. If you ever wanted to look up any Java programming, and also JavaScript too, he would be a great resource. So he described actually reactive programming and functional style as really a beautiful way of doing things. It fundamentally has changed the way how we do programming, and it is very true. So as you can see in here too, so we're doing, okay, back to this, we're doing processing the stream. We tell it to, give it a function map, and then we immediately need to consume the data. So then we use, in this particular case, the subscribe is like a client, right? I'm going to consume what's going to come out of this operation. So the subscribe is right there too. You don't need to create another statement. It's basically you chain it, you say dot subscribe. And in this particular case, the dot subscribe will essentially take whatever is there and do a print. So using this particular example, Timber is just a library to print it out to the console. So doing a .d, it would just print out items, equals, in this case, would be, 1 will become 10, and then 2 is 20, and 3 is 30. So that's what you'll find out. So that's a kind of a quick example of a reactive programming, using this Rx Java. Now, Rx Java too has many operators too. In fact, RX Java itself is about maybe at least 250 operators operating, different things, right? We're dealing with create operators. We're dealing with like filtering, transforming the data, and categorizing, and then also some are like dealing with time sequence and different things. So there are like 250. But if you look at the whole reactive extension, I think it's like up to almost like 500 different ones. So you can see it gets into a bit too much. So there are also like new libraries that come out to kind of aim at trimming that original RX operator set. But the thing is too, the RX operator is definitely a very rich set of operators. So. Okay, so that's enough about reactive programming as like a quick intro. So let's take a look. So now we get into reactive systems. So when we look at reactive programming, we're talking about some specific mechanical way of dealing with a particular some routine to kind of operate on some data. So you are kind of very much kind of focused on like say one component of a larger system. Now, in reality, when we're dealing with especially systems that are complex in an enterprise world, right? We're not just dealing with one component. We're dealing with many. So now in today's world, we're also talking about microservices and all these things. And so the idea of microservices too, I like to also bring up here, is kind of very much in line, with the concept of reactive. Reactive too advocates a very loosely coupled type of system, which means that you have components that they are all running independently, right? In an ecosystem of many things. So an example would be like an e-commerce system. So you can have e-commerce systems, and that's a perfect example of a candidate for microservices, reactive microservices too, because it emphasizes all of your functionality as being very distinct. So now this is just a very crude kind of example. I'd say e-commerce. Let's have an order microservice that does the order, and then we can have another one that does like processing payments, right? That's another good component. And then we have like shipment, or maybe the inventory has another component, and then we have shipment and delivery and shipment, and then counting, whatever you want to call, right? That's kind of essentially a complex ecosystem is like. So the thing I'm kind of talking about this is because, and here's the thing. So in reality, we're dealing with many components in an ecosystem. So reactive systems are really essentially dealing with systems as a whole. So that's what reactive systems is. So as you can imagine, right, if we're dealing with a single thing, if we're saying in an Internet of Things and IoT situation, we only, let's say, have one device that are collecting some temperature, right, for example, then that's easy enough. But how about, there are cases in which an IoT, installment of many devices on a farm, like a farmer has a big 2,000 acres of land, and he has planted crops everywhere, and he wants to be able to monitor, the temperature, maybe water, whatever he wants to monitor. He can install all of these, devices that actually has an internet sensor that can sense data, IoT kind of data. So under those kind of systems too, you do need like better ways of handling your system. So so that's when reactive systems come into play. And okay, so I have kind of veered off enough, and so now let's get back. So reactive systems too, essentially there's this manifesto, is a guideline that's come out of Lightband, the company Lightband, in which Dr. Martin Odersky, inventor of Scala, he started Lightband, and he also then developed Akka, the reactive library, very sophisticated. And so, yeah, that's the Scala company, but they also have been more like leader in the reactive space. And so they also have led the effort of defining a set of principles to guide and define what reactive systems should be. And so that resulted in a reactive manifesto. And it's essentially, if you talk about reactive manifesto, it outlines and kind of provides the 4 tenets of what a reactive system should be. So first and foremost, like going to there, this is a kind of a very typical diagram we show. So it's basically systems needs to be very responsive. So by saying responsive is that request comes in, so all of your response needs to happen in a very timely manner. That's what responsive means. And now, in kind of, let's say, again, going back to imperative, you may say, well, why do we need that? Okay, so if you are just learning how to program, usually we only deal with maybe like one thing. We're doing some requests, sending to the web server, and then expecting the web server to come back with some response. Yes, that's simple enough. But again, in reality, we're dealing with big e-commerce systems. We're dealing with Amazon, right, for example. And how about this? E-commerce systems for ordering flowers, right before Valentine's Day. And so you can imagine the volume of data all comes in all at once. So those kind of scenario, you want the user, all of these orders to come in and be kind of processed in a very timely manner. So anyway, so that's responsiveness. So, and now move over to the right hand here, right? Over here, the resiliency. So when we talk about resiliency, it means that if there's any error condition that occurs, say for example, in a cloud kind of clustered environment, you could have like many processes running too, right? They're clustered, they're all kind of high availability. So let's say you have some error that happens. Some components, all of a sudden you have 10 nodes in a cluster, and then 5 of them all of a sudden drop. And it needs to be able, the system needs to have a way of able to bounce back. So that's what is meant by resiliency, so that the overall, your responsiveness should not suffer. So I just now mentioned about Akka, so that actually Akka has a very good mechanism of handling some of these kind of error condition and able to have your systems bounce back really quickly kind of thing. So now I won't go into all that detail, but just to give you an idea. So that's resiliency. And then if you go over to the left side here, there's elastic. So by saying that the system is elastic, it means that if there are many requests coming into your system, then the response, you can't, you can't really, kind of degrade the system in that case. So your system will become very elastic. It's like an elastic band, right? You can stretch it, you can kind of like pull it back and forth, and it, if there are more processing happening, then you need or actually more requests happening, then you will then need more processors to handle all of these requests. And that's kind of elastic. And then if there's during downtime, right? Okay, take example for Valentine's Day. So if, right before Valentine's Day, you get a lot of requests. So that's when all your system needs to be, kind of in full, everybody, on standby, everybody be ready to do work, and you kind of utilize all the processes that are available. However, during downtime, there's not as much order, then you can kind of shrink back and return a lot of these processes back to the pool, or kind of make them idle. So then you don't need that many, kind of processes to be running. Now, especially in a very, cloud-driven world these days, when, like using, let's say a company, I'm actually a cloud user. All my systems run on the cloud. So that is very important. You do want system to be able to kind of adjust the load accordingly. So then you don't get charged, because in a cloud environment, you tend to be charged the amount of time you utilize the processor to do your job. So you do, in that case, to kind of stop, you do want to, you basically want to like stop the processes that are not running, so then you don't get charged, for being like just running without actually needing to be run. So anyway, so that's that. And then now, let's get to the message-driven, the fourth kind of tenets. I tend to say, kind of like the last one, and not to say message-driven is not the main thing, but actually, in my viewpoint, is that the message-driven part of the requirement is essentially the mechanical way, right, of enabling a system to be responsive, to be resilient, and to be elastic. So that's sort of like a core kind of capability that has to happen, that has to present in a reactive systems. So, okay, so enough of me then talking about the reactive manifesto, but just again, this again will be the 4 principles for a reactive system. So, okay, so now then let's move on. And here, that's just a picture too, showing you reactive streams. So you'll be running like, what's that? Reactive streams? Okay, so here we are, right? So during again, when we are talking about reactive streams and reactive systems in general, they are being utilized in situation in which we're expecting high volume, high load, high stress volume going through the system. Okay, and so now reactive streams, the purpose of it. Okay, first of all, what is reactive streams? So it is actually a specification that comes out of all of the reactive kind of vendor library, kind of provider, right? So it is a standard that essentially define how asynchronous data streams ought to be managed, in a reactive system, so that there won't be buildup of any back pressure. So anytime you think of reactive streams, essentially is what it deals with, back pressure. So we use this example as a guy, being sprayed all the water. It's like essentially that's what happened, right? If you do not manage your back pressure very well, then streams of data coming in is basically, think of this guy as the guy supposed to be processing these, and he probably will be all, this processor will be completely overwhelmed if you have too many requests coming in. So that's what it means, is essentially the back pressure kind of build up in this case. So this is just a picture to describe reactive streams. And again, it is a specification that guides, how back pressure should be handled. And then you might be wondering, like, why need the reactive streams? Now, think of it that way. If all of the vendors are implementing reactive systems, then, and essentially, if we're talking about data, flowing through a system, right? So now, the thing is that if you say that, I'm actually, let's say Akka. Akka has this way of handling back pressure, right? So there's also like, anytime we talk about streams, we're talking about messaging systems that are dealing with publisher and subscriber, the pub-sub kind of model, right? It's essentially data events, get published, right? With it comes data published. And then there are subscribers that are consumers for these data, right? That happens. So a pub-sub system. So anytime you have this happening, then you basically have to like handle the data correctly, accordingly is what it is. So yeah. So anyway, so and then of course too, I'm sorry, I lost kind of a train of my thoughts for 1 second. But yeah, so it's essentially two reactive streams is important because then you have this specification so that all of the library implementers will be able to follow these guidelines and implement this stream according to spec. And so the good thing about it is that if you think of it, right, is that, let's be creative too, is that, as the world is getting more and more complex, right, you have, let's say you have different way of implementing a system and handling all of these different data. But then the thing is too, you can have different languages, different libraries that are handling different sets of data, especially in a big corporation. You can actually have different types of system operating differently, but yet you want all these systems to be able to talk to each other. You want system A to be able to talk to system B. Okay, maybe use an example. Some employee data that probably is from a human resources department that probably goes into another department. Engineering department might have kept their own copy of some of their team members, information. Then you might want, one system to talk to another of your human resources data to kind of somehow sync up with the data that's kept in by your engineering department. So you need to have some ways to kind of make those data talk to each other, right? And, for whatever it is, it could be some time in which, that's an example that I'd say doesn't demonstrate any urgency for, heavy processing. But let's say you have systems that are even like an e-commerce system, for example, like you have customers, right, that needs to order something, and then they want to be able to process their order, and order needs to also be, kind of the payment part needs to go to another system. Those type of things, right? You may have like too many orders coming in, and then you also have another system maybe written by another languages that are handling all of these order information and the payment, managing all of the payment. Those kind of things. So you could have like different systems, right? One is written in Akka, the other maybe in older mainframe too, even. So you can actually essentially have two sets of data be able to talk to each other, perhaps through some pipeline. You pipeline all these data together, and then you will need some ways of handling back pressure between them, because you don't want any one part of your pipeline to be overwhelmed with all of the requests that are coming in, for example. So if you have kind of like a common set of guidelines, then it will make the communication a lot more easier. So that's the ultimate goal. So okay, so that's reactive streams. I think I talked enough about that. So let me then go into the next one. In this case, did I go? Okay, so now let me go back now to say that, well, what problems are we trying to solve, right, using reactive systems? So you might say, well, I don't really need reactive systems. Now, that is very true. You don't necessarily need reactive systems, and reactive systems is also not for everything. So what are the problems, right? So fundamentally, it's that we're dealing with systems that have to handle concurrency. You want to be able to handle, multiple processing, right? And there's concurrency, there's also parallel processing. But don't get the two mixed up, because parallel processing always require hardware. So in general, if you have multi-CPU, and then in that particular case, like you can then have like CPU. Each CPU is handling different tasks all at once, right? But the thing is with concurrency is that we tend to be a bit more like less luxurious of having too many CPUs available, processors available. So in a in a concurrency system, very often is that we give the illusion of parallel programming. Now, if you are come from a computer science background studying operating system concurrency, then you probably are aware of the fact that then in very often too in concurrent systems, we talk about threads, right? So now as such too, threads are not easy to do, especially if you've done it before, and I myself have done it before. It's really hard in the sense that you cannot, easily, let's say even like debugging and stuff like that, because normally, right, traditional programming is that we do everything all in sequence. So when we debug it, we follow the lines of code, right, and like that. However, think of like in asynchronous programming, we're trying to handle it using threads. And so in that case, we have different threads, but the thread too, you issue a command and some threads go off and does something and they have their own scheduling schedule, right? Some of them threads could be sleeping and they can be like, dormant, or if they can be like awake and doing some things. And it's very hard because you can run into problems such as deadlocks, race condition, all these other things. So anyway, the point I'm trying to make out is that reactive systems is kind of nice in the sense that it hides all of these complexities. So then, from a developer point of view, we don't have to deal with these lower level kind of, more primitive, so to speak, kind of processing. Because then we're letting the reactive libraries to handle all of these things for us. And that's the advantage. And then, of course, now I also talk about asynchronous processing and distributed systems. And these are really fundamental problems that any distributed systems have to deal with. We're not talking about monoliths now. We're talking about systems that are, composed, complex system composed, of many components, and they are all distributed. They can be everywhere. And what would even be more complex is that if you bring in the database, right? So sometimes too, if we're dealing with data that travels from one system to the other, there's no need for you to keep track of it. You don't actually involve a database or something. That's not as bad, right? Those are called stateless kind of operation. You don't need to worry about it. However, in reality, right, especially say with an e-commerce system, we have certain data that probably you need to make sure that you don't corrupt the data when it travels from the order system, and then some data goes into the payment, and you need to do all these verifications. So can you imagine the statefulness is also extremely important. So now reactive systems by itself may not solve the stateful issue problem for you, but the thing is too, is that because of the nature of it, and then also there say, for example, there are other capability that works hand in hand with reactive systems to handle, for example, like stateful things. And also, not only that, now we're talking about data crossing different boundaries, right? We're from one processes to another, to other geographical areas. And this is the time too when cloud native also comes into play, because then we're dealing with systems that are replicated. We're dealing with data that's also even being replicated everywhere. So, okay, so you can imagine myself talking so much already. So let me move on. Okay, so now I actually have already talked about most of these. So reactive use cases. So what are some of the kind of perfect candidate for utilizing a reactive approach? Now, first of all, also kind of make sure that to know that reactive, kind of the enterprise level reactive Java is not for everything, right? If you're just doing something local, small, if you have a small department, you're handling maybe just 100 customers, you don't have multiple requests coming in, then in those cases, most likely you do not need a reactive kind of systems. If you don't need to handle commerce, e-commerce and those things, then probably you don't really need it. So if you just need it for more like storing address information, storing some information, looking it up, then most likely no need for it. Now, for reactive use cases, what are good for it to use? Now, as you can see in this list, I have AI, artificial intelligence, machine learning, big data processing, IoT, which I cited an example earlier about a farmer using those devices on the field, dealing with many devices. You're trying to collect the data, weather data, and sends it to a data or server somewhere, edge computing, and e-commerce. So these are like really perfect use cases. The idea is that you have tons of data coming in, the huge volumes of data. How do you manage the back pressure, right? You don't choke your system, that type of stuff. So those are kind of candidates that are perfect, for example, for using reactive approach. So, okay, so that's that. And let me kind of go to the next one, which is like then bring to the question too about cloud computing and reactive. So when we talk about cloud computing and reactive these days, are really about cloud native ready. Now, what is actually cloud native? It just means that your systems, again, you're not only dealing with one component of your system, you're dealing with many components, and many times too, you also want to make sure there's high availability, they're clustered and everything. And so they need to be cloud native ready. So they do require different sets of capabilities or way that you can manage them. And so now in today's world, of course, now we have cloud, and very often too, which I actually didn't even say in here, is like containers, right? Containerization. So that's a very, I'd say even like the standard way of handling all of these applications that are running in the cloud. It's really through containers, because it's just logical, right? You have everything is all wrapped up in a container. The container itself is a self kind of carries with it like an operating system. For example, like Docker, that's a very commonly used Docker container technology. There's also Mesos, for example. There are other ones too, but I'm sure a lot of you have used Docker because that seems to be the most popular. And then also using them on Kubernetes. And then now it's IBM too. I work for IBM, and so there's also Red Hat, which is also our kind of brother or sister company, however you want to say it. So Red Hat also has OpenShift too. So OpenShift is built on top of Kubernetes. And the nice thing about it is that it is a value-added kind of Kubernetes service, more provide you with more capability in there. So that's also an example. Now, if you're interested too, I have my contact information, because I'm also doing a couple more talks too, and deeper workshop if you're ever interested in it. I invite you to join me too, and I have some more information for you later. So anyway, so these are some of the things, right, that when we talk about reactive, they can also be kind of very much reactive works very well, in a microservices kind of approach. Then also, like we're talking about serverless deployment, those kind of things. And so again, the cloud native ready is definitely cloud native ready. So, okay. Oh, sorry. I think I went. Okay. So now, the last but not least too, and before I get into some code, is that these are like a few very popular reactive libraries and toolkits, if you're ever interested. So I mentioned about ReactiveX, and then I wanted to also point out, there's also Akka that I mentioned about, right, in the bottom here. And then there's also, I mentioned about RX Java, the RX extension. There's also a newer library that came out, essentially the Red Hat folks that work on. It's called Small Rye, Mutiny. This actually, Mutiny is the new name. So essentially too, they don't claim to like replace RX, the RX operators, but they essentially are similar to what the RX operator does. It provides a set of operators, but it's more trimmed down. So as I mentioned, RX Java has 250 or so operators, but Mutiny has kind of, I didn't actually count it, but I think it's definitely, they are smaller, and it's not as confusing, because I think it's just from the experience of using RX, the RX operator, they realize that a lot of them can actually be kind of more efficient, made more efficient. And they also have the concept, just like the Spring reactor. If you're familiar with Spring framework, they have mono and flux. So in Mutiny, they also have the concept of like kind of similar to mono and flux, and they call it a uni and multi. So they're kind of similar. So anyway, so that's something I like to point out. And then there's also Eclipse as a Vertex library that's also highly efficient, which I actually have done some work on too. Then there's also MicroProfile, which is currently my team is working on its open source project, and is ready for cloud native, for microservices, and very lightweight. It's really targeting for enterprise kind of application usage, but it's a lot simpler than what used to be enterprise Java Beans too. And okay, so now let's look over here too. What I did not mention is RSocket. RSocket is reactive socket. It's a reactive foundation, which is actually underneath the Linux Foundation. Reactive Foundation has this reactive socket, RSocket library. It's a lower level library. It helps you to code on the level 5 and 6, kind of, so a bit like lower level kind of the library that you can use, but it's very efficient and gives you a lot of flexibility too. But the thing is too, I have to say, I'm also doing a talk with another speaker, co-speaker. What we found out is that our socket is only like a year and a half old. So some of the things too may not be as easy to use. So that's what we found out. It's probably because it's still in an early stage library, but it is very promising. So if you ever look into, perhaps, in your connection too, you can be using our socket as opposed to HTTP, for example, something like that, right? So, okay, so that's that. And then there's also Microsoft has a library called Orleans too. So maybe some of you have worked with it too. So I just wanted to kind of point out to you so you get an understanding of that. So, okay, so now let me kind of jump into, let me see how much time. I think I'll just kind of do this and then get to my code, showing some of my code. Let me see. And I just want to like quickly show too. I know I was just saying that from imperative to reactive. So let's kind of give this a try. I just want to quickly show you something. For example, right? I mentioned about Vertex. So I do want to show you some Vertex code. Wait, I think I brought up not the correct one. And here we go. So this is just an example. I know it's kind of got a lot of things, but let's take a look at as the simpler one, I should say. Nothing is simple these days, but let me kind of take a look at this. So this one essentially too is a, let me kind of look back over here. I'll look over here. Okay, so this is a Vertex example. So Vertex too, what it has is it has what is called an event bus. So the event bus and also a model, it's called abstract vertical, a vertical model. So in code, on the code level, you do want to extend it if you want to use it. So what I've done here is just a hello world, but using the vertical way of doing things, the vertical model. So what you do is that for that you want to, it has a method called start. So anytime you want to use Vertex, you can do a start. And basically okay, let me kind of go back here. So if you're familiar with Java, right? So all you need to do to bring up the Vertex runtime. Now we're not talking about the cloud. Just say running Vertex in its own runtime on Java. And so what you can do is you can just do Vertex and then do a .vertex, and that essentially will bring up your runtime. So not complex at all. Then what you want to do is that then you want to do is a deploy vertical. And then in this case, deploying vertical. For example, I'm doing a hello world. So my hello world, I have to extend, essentially, I'm utilizing the model, and it's not a must. You do not need to always use the vertical model, but that's just a recommended way, especially if you want to talk about deploying this onto the cloud or even just deploying into runtime is a lot easier to manage. So over here, the start method will then, I'll just show you if you want to set a timer. you can then use the runtime here has a method called set periodic, and then all you need to do is just set the timer. In this case, it's a 5,000 milliseconds, which is equivalent of 5 seconds. And then in this particular example, I'm just saying that, okay, print out the word tick, and that's all. And if you want to actually start an HTTP server, you basically in Vertex 2, you do want to use a handler to handle all your requests. So my request handler over here, all I'm doing is print out the logging information. And essentially too, over here too, I have the request, and then I basically say on the response side, I just send back the word hello. And then I also then listen and basically bind this HTTP server to listen on port 8080. So that's how you start an HTTP server inside your Vertex runtime. So that's just as simple as that. So yeah, so that's kind of just a quick example to show you. And again, if you look at this too, this is the kind of functional style of programming in Java. But I think in, say, JavaScript, there's already get that kind of capability. But in Java, it started, right? In Java 8, we can use this kind of chaining of command kind of way of doing things. So, okay, so yeah, I think I may actually already be almost over time now. So I just wanted to thank you all for having sat through my talk. And then let me then go back to giving you some more information. And where is my slides? Okay, here we go. And let me run this again, play from the current slide. Okay, and I just wanted to thank you all for coming to my talk. And I wanted to also invite you to join me. I do run a live coding stream on Twitch, and that's on the IBM developer channel every Wednesday at about 12:45, that's US Central Time. And we also have other members of the team. Right now, I think there's been a bit of a rescheduling different people. So there will be other streams too. So if you're, say, interested in Kubernetes, in cloud stuff, we have folks doing that. There's also a lady who's doing like interviewing IBM champions. If you're ever interested in IBM technology, wanted to learn more about it, and also seeing some of these folks who are helping with using our product, there's also a show with that and different kind of things. So please kind of tune into that, and that's how you can find us, the twitch.tv IBM developer. And this how you can contact me. And thank you so much again. I want to point out I have a Discord server, so you can scan this QR code if you'd like to join me on Discord. I welcome to our conversation, to continue with the conversation. Basically, too, I hope I can pique your interest in not just like reactive programming. There are just so many things to do with like heavy like computing world. There's just so much creativity that can happen. I'm all excited about it. So, okay, so please connect. And then I'm also on Twitter, so follow me on Twitter. This is my GitHub repo. I also have a blog site is on dev.to. And then that's my profile on the IBM developer. And then if you want more information on reactive systems, this is the link on our developer.ibm.com, technologies, reactive systems. And then these links too, these few are essentially the reactive manifesto, the reactive streams, the reactive foundation, and some information on reactive design patterns. And this is our IBM developer website where you can find tons of other information, not just reactive. There's AI, there's cloud, open source, you name it, right? There's Watson, and it's just even like quantum computing, and anything you need, you can find. So with that, I think I am all done with the talk today. And if you like to stay in touch, I welcome you to do so. Thank you so much.